Hello everyone. In this video we are going to talk about the energy of a system. We will learn the basics of the energy analysis, some basic types of energy, conservative and non-conservative forces, and finally we are going to learn how the scalar product of two vectors carried out, because the scalar product greatly helps us during our engineering education and professional engineering life. Here I'm going to give you two different definitions of energy. In the first one, the energy is described in a more general way, but in the second one, the definition is given from an engineering perspective. In the general definition, energy can be defined as the strength and vitality required for physical and mental activity. This is like an everyday definition of energy. And in physics and also in engineering, we define energy as the capacity to do work. In addition to these two definitions of energy, of course you can find lots of definitions regarding the energy and from a variety of different perspectives. For example, a chemical engineer will probably choose more suitable definition of energy for their work. Or a nuclear physicist may prefer to define energy in their own terminology. And of course, no matter what the definition is or how the definition is made, they all are referring to the same concepts. The most basic and most fundamental way to describe energy is that we have here the capacity to do work. And in order to carry out the energy analysis, we should define a system. When defining the system, we will be deciding to what effects to include or what effects to exclude from the system. Obviously, we are not able to include all the universe in our systems. Our system may be a single object or a part. It may be a collection of objects and particles. It may be a region of space, for example, the interior parts of a car. And finally, its size and shape may vary. For example, a water-filled balloon hits a wall, it will deform, its size and shape will vary. And when defining systems, we also define a system boundary that separates the objects of the system and the surroundings from the system. For example, in this box and ball example, dashed red lines are representing the boundaries of the objects that constitute the system. And let me draw another boundary. And let's say this orange boundary is representing the boundary of the system. Not the objects, but the boundary of the system. So the system boundary separates the object that constitutes the system from the environment. Again, it doesn't have to be coincident with the boundaries of the object, but there is only one restriction. The system boundary has to include all the objects or particles in the system as a whole. In order to make it clear, let me give you one more example with the system and the object boundaries are coincident. Here in this example, as you can see, the red lines, dashed red lines representing the object boundaries and the orange dashed lines are representing the system boundaries, and both are coincident with each other in this example. Okay, let's talk about work and its definition. From a physicist's point of view or an engineer's point of view, the definition of work is quite different than the definition in our everyday life. In our everyday life, running some errands can be defined as work, or going to an office place to conduct some business tasks can be named as work. And to understand the difference between the definition of work in our everyday life and definition of the work in physics or in engineering, consider yourself, for example, while standing still in your living room. And imagine you stood there for an hour, and during that time, your muscles provided support for your body, and you crossed your arms for an hour. Again, the muscles in your arm also provided a support for your arms to be stay crossed. You may think that my muscles has to be done some serious work on my arms. Similarly, my leg muscles have to be done a considerable amount of work on my body. But in physics, that's not the case. In physics, a force does no work on an object if the force doesn't move through a displacement. So let's consider another three cases from my example. In the example, I have a block that is placed on a surface. And in the three cases, the force F applied to the object from different angles. In all three cases, the magnitude of the F is the same. I know that you can all say, in the case 1, the object will move further than the other two. Case 2 will be the second one in terms of the displacement of the object. And in the case 3, of course, there will be no displacement. The work done on the case 1 is the greatest because the F in that case was purely horizontal. Therefore, it caused the object move further than the other two cases. In the second case, the force F has two components in the vertical and horizontal directions. Therefore, some of its magnitude is in the vertical direction. Therefore, we have a less amount of force in the horizontal direction, and consequently displacement of the object is smaller than the first case. And obviously in the final case there are no force components in the horizontal direction, therefore the object did not move. So if you want to line up those three, we will have a sequence like this. Here from this example we can deduce two conclusions. No matter how much energy you spend to apply force on an object or a particle, if the force that you have applied to that object is not moving, you will end up with a zero work. And the second conclusion is, even if the magnitudes of the force are the same, you obtain different amounts of work depending on their angle of action. Okay, to wrap up the subject, let's express the work mathematically. Work is equal to F times delta R times cosine theta. Here, delta R represents the amount of displacement, and here the angle theta is representing the angle between the force and the direction of movement. Just for looking at this equation, you can deduce the results that we have talked about. So if the theta, the angle, is 90 degrees, this will be equal to 0. So there will be no work. And if the angle is equal to 0 degrees, then you will get the most of it from the force applied to the object. Okay, what about the dimension of work? Here I have newtons. Here I have meters. And the cosine theta has no units. Therefore, the dimension of work is equal to Newton times meter. And the combination of these two units, Newton times meter, has its own name. The combination took its name from the famous physicist James Prescott Joule. Equation here, in fact, is an alternative form of a special vector operation, and that vector operation is called the scalar product. Let's take a quick look at how the operation is carried out. We use this dot to define scalar product, not a dot on the ground, but a dot right between the vectors and at the center of the vertical height of the letters. And like I said before, the scalar product is an equivalent of the multiplication of their magnitudes times the cosine of the angle between them. As you can see, this equation and this equation are very similar, and we are going to use the scalar product often to carry out such operations like calculating the work required. So what are the properties of scalar product? Scalar product is commutative. You can alter the order of the vectors and you will get the same result. And you can distribute the vector into parentheses. Okay, before finishing this section, I'd like to mention some other applications of scalar product that are very important. Let's take a look at how do we apply scalar product to unit vectors. Take the I component, I vector, as example. I scalar I. Please recall that the magnitude of a unit vector is equal to 1. And we said that scalar product means that you take the magnitudes of two vectors and then you multiply them with cosine of the angle between those two vectors. And here we know that the unit vector I and the other unit vector I are lying on the same axis. Therefore, the angle between them is 0. So I have cosine 0 here, which is also equal to 1. Therefore, I times I is equal to 1. Of course, scalar product of all three unit vectors are the same. They are equal to 1. So what if we take the scalar product of I and j? By the way, here I forgot to use absolute sign to I forgot to tell. By the way, here I have used. By the way, here I used regular parentheses, but by the way, I used regular parentheses here. Now I changed them to absolute signs because the absolute signs in vector calculations designates the magnitude of that vector. So again, magnitude of I times magnitude of I times cosine 0, which gives us 1. Okay, let's go back to scalar product of I and j. Magnitude of I is equal to 1 times magnitude of j is equal to 1 times cosine 90 degree. Here I have 0, of course, and the result will be 0. If we apply the same procedure to other unit vectors, the scalar product of I and j, the scalar product of j and k, the scalar product of I and k is equal to 0. So let's use these two expressions to calculate scalar product of two vector in 3 dimensions. I have vector a and b, and both of them has 3 components in 3 dimensions. And those components are defined with the magnitude of the component in the x direction, in every direction, and the unit vector in that direction. So if we calculate the scalar product of those two vectors, we'll get ax, bx, ay, by, az, bz. I advise you to calculate this scalar product all by yourself using this expression and this expression here, and distribute the components of one vector to other and try to obtain this result. Be careful, even though we are multiplying two vectors, we ended up with a scalar. Okay, that's all for this video. In the next video, we will talk about different types of energy and conservative and non-conservative forces. See you in the next video.